Lesson 1.4 in PreCalc. The learning targets for this lesson are for you to be able to identify extrema, including relative and absolute maximums and relative and absolute minima. Also to be able to use those extrema to describe intervals of the domain for which the function is increasing, decreasing, or has constant behavior. In the explorations that you completed in class, you should have been able to figure out how to find the relative and absolute maximums and minimums on your calculator. Just as a review, some key concepts that are also in your textbook talks about the relative minimum being different from the absolute, or relative maximum being different from the absolute. The absolute is the absolute highest point on the graph. The relative is the highest point among the points around it. So we have two peaks. The highest peak is the absolute. The lower peaks that are not as tall as that are the relative peaks. And the same thing with minimums. The absolute minimum is the lowest point, and the absolute maximum is the highest point on the entire graph. Everything else is a relative minimum or relative maximum, lowest on a recent interval or highest on a recent interval. End behavior is something that you studied in Algebra 2. It's what happens to the y value as x increases infinitely as it gets bigger and bigger, or as it decreases infinitely as it gets smaller and smaller in a more negative direction. So we get more and more negative. Algebraically, we will create an xy chart, pick an x and y, pick some larger values of x as you did in your exploration. So we're going to look at that in this one example. We have this function. It is a cubic function, so some of you from Algebra 2 already know what the end behavior is going to be, but you also have to be able to provide evidence in a table. So we have this cubic function. I've typed it in exactly as it appears there, and I'm going to go to the table, and again, you want to make sure that this is set for table set independent ask for you to be able to put in the values. And I'm putting in 110, 100, 1,000, 10,000, and I'm getting very large numbers. 1,081, so it got larger. The next one is 1.01 e to the 6th. When I highlight that value, I can see the exact number is 1,009,801. Then I have 1 e to the 9th. 1 times 10 to the 9th, and lastly, roughly 1 times 10 to the 12th. If I had more space, I could write those digits out, but I'm not going to. Again, I can highlight them on the table to figure out what the exact number values are. Next, we're going to test -1, -10, -100, -1,000, -10,000, and this gives us 3, -879, -9 times 10 to the 5th, -1 times 10 to the 9th, -1 times 10 to the 12th. So these are decreasing, very large values, right? It's getting larger and larger in a negative direction. So the idea is it's going to get infinitely larger. If we were to look at the graph of this function, we could see that end behavior, that as it goes to the right, as we keep picking numbers out to the right, further and further, just as our table showed, even as far as 10,000 out to the right, which isn't on this graph, it just keeps getting larger and larger. So as x approaches positive infinity, that's as we move to the right on the graph, f of x is also increasing infinitely. So it's going to have positive infinity. And as x decreases infinitely, that's what the negative infinity means, as it decreases infinitely, so going to the left infinitely, we can see that we're getting larger and larger negative values, so f of x decreases infinitely, the output decreases. So this talks about x moving to the right, this talks about x moving to the left. In this case, it's going to continue rising infinitely, in this case, it's going to continue falling infinitely. We're going to estimate and classify the extrema for the graph. When I say estimate, I don't mean, oh, take a guess what it is on the graph. I mean use the graphing calculator and round to the nearest, often the nearest hundredth, sometimes the nearest thousandth, We're going to do hundredth for now. So we have this function right here. We can see that it has a relative minimum and an absolute minimum, and a relative maximum. It has no absolute maximum because this graph continues up infinitely. It is a fourth degree polynomial function, a quartic function. So we're going to plug in x to the fourth minus 5x squared minus 2x plus 4. And we can see that graph. If the graph doesn't fit on our window, we can rescale our graph so that we can see the graph. I'm going to do second trace, and I'm going to look for the minimum values first. I'm going to move my cursor to where I believe that relative min is and go a little bit to the left of that relative min. And then it says right bound, I go a little to the right and hit enter. And then hit enter for it to bounce back and forth and get the value it can come up with as the relative min. So this relative min right here is negative 1.469, so I'm going to round it up to negative 1.47. Its output or height at that value is 0.804, so 0.80. This is a relative minimum. This absolute minimum, I'm going to calculate now. And so I hit second trace, go to minimum value, go over to that, a little to the left of that point, and then hit enter, and then go a little to the right. And so I'm going to, on my calculator, whoops, let's get rid of that screen. It says right bound, go to the right, hit enter again, let it guess. The absolute min is given to us, it's even highlighted on there at 1.672, so we round to 1.67, negative 5.506, which is negative 5.51. There's the absolute minimum. We still have to get this relative max up here, relative maximum. So we're going to do trace, or calculate second trace for calculate maximum. We're going to go to the left of, it says left bound question mark, go to the left of where we believe it is, to the right of where we believe it is, hit enter. The calculator will bounce around until it finds the relative maximum there at negative 0.203, so negative 0.20, and then 4.201, so 4.20. So we have our relative max, our absolute min, our relative min. For our other function, x cubed plus 2x squared minus x minus 1, I'm going to go to the graph, and I can already see that it has no absolute maximum because it goes up infinitely, and it goes down infinitely, so no absolute minimum, but it has a relative max and a relative min. So I have my relative max and my relative minimum. So I'm going to trace, by the way, this is all fitting very nicely on the calculator, but if I couldn't see them, let's say I saw part of it, I could zoom out or zoom in or change the window to affect the height and width of the graph if I needed to. So we're going to do second calculate. We're going to do the maximum first since that's the first one we come across. So I'm going to go to the left, go to the right of it, hit enter, hit enter. The relative maximum is at negative 1.548, so negative 1.55, and the height is 1.631, so 1.63. Second, calculate the minimum, the relative min. I'm to the left of it, I'm to the right of it, hit enter. I have 0.215, so 0.22, and negative 1.112, which is negative 1.11, negative 1 and 11/100ths. So I've got my relative max and my relative min listed for this function. This brings us to, these are the very important points where the graph actually changes its behavior. Instead of decreasing as I go from left to right, so we think of it as I've got a little person here and they're walking from left to right. Remember, you did this with slope when you were in middle school, figuring out whether it had a positive slope or negative slope. Same idea here. From left to right, I'm going downhill, and then I hit this relative minimum, and I start going uphill, and then I hit this relative maximum, and I start going downhill again. I hit the absolute minimum, and I start going uphill again. These points, these extrema, are also called inflection points. A point, and it doesn't have to be an absolute or relative max or min to be an inflection point, but often they are. where a point where the graph changes shape or its behavior, but is not increasing or its increasing or decreasing behavior. I don't really like how that is worded right there. It does change whether it's increasing or decreasing, but not necessarily. Sometimes it could change its behavior and just be constant. So the point is here that it could be increasing or decreasing, or I don't like the word changes shape. I would just say changes its behavior. An inflection point is where it changes its behavior. Here it was increasing as the person walks from left to right, and then it stopped. They walked a flat plateau. So the behavior changed at this point. At this point, they then began decreasing. So that is another inflection point. When we look at those inflection points, they help us talk about the domain. Over which parts of the domain is the function increasing from left to right? Over which parts of the domain is it constant? And over which parts of the domain is it decreasing? So when we take a look at this inflection point here, whatever this x value is, let's call it x sub 1, prior to this inflection point, it was increasing. Even at this inflection point, it's increasing again. It did a brief turnabout here. That's still an inflection point. The behavior changed slightly, but it didn't change from increasing to decreasing, and it didn't even change to constant. Still considered an inflection point. I'd like to go back to give an example and then have you try a couple of these as we look at estimating intervals. Going back to these problems, because we already have these points where the graph changed its behavior or did something odd at those points of inflection. It's the x value. We're talking about the domain, the intervals on the domain, the x value that we're looking at. So as this person's walking from left to right, they're starting up here, this function is decreasing as far left as we could go, which is negative infinity. So we have the function is decreasing along the following intervals. Along the following, we don't write this, but it's x intervals. Because when we talk about decreasing, we're referring to the height of the graph. The height is coming down on the graph as we go from left to right if it's decreasing. So that is from negative infinity all the way up to this x value, where then it starts to turn and come upward. And that is negative 1.47. It's also decreasing from here to here. That x value is an x value of negative 0.20 all the way to this x value, 1.67. I don't want to use the y values. The y values are the height of the graph. I'm talking about the height decreasing. I don't want the height. I want to know from which x to which x is it decreasing as I walked left to right. From negative infinity to here, and from here down to here, it's decreasing. So those are my decreasing intervals from left to right. My increasing intervals, I don't have any constants on this graph. My increasing intervals are from here to here. So I have to talk about which x's. Where did that start? What x value did it start increasing at? Well, the point of inflection, which was negative 1.47. So negative 1.47 all the way up to this relative max at negative 0.20. And it also, wait, I have the or, not the and. I should be having an and here, sorry. And it also increases from this absolute minimum, and then the rest of the graph increases, so to infinity. That absolute minimum had an x value of 1.67 and goes on infinitely. Now I don't have equality with this because that point of inflection is considered not to be increasing or decreasing, but the point where the behavior changes. So that's why I'm using parentheses and not brackets. On this next function, the one to the right, we have a relative maximum. Prior to that, our person is walking uphill. And then after this relative minimum, the person's again walking uphill. So from negative infinity up until this x value on the relative max of negative 1.55, we are increasing, the height of the graph is increasing. From this x value, which comes from our relative minimum, we have 0.22, to infinity because it doesn't stop increasing after that x value as we move to the right. For the decreasing behavior, and I realize I swapped these colors, sorry. From this relative max to this relative min is the only place on this graph that is decreasing. So this relative max is where the decreasing started at negative 1.55, and the decreasing stopped at 0.22 at those points of inflection. Once again, using parentheses, not brackets. This is supposed to be a parenthesis because it doesn't, that point is neither an increasing or decreasing point, it is a point of inflection. Please try this for these three graphs, these three right here. All right, I went through and I did this on my calculator. I found, even though I could see it on this graph, I still did it to make a point with a couple things. And on these, I couldn't see as well for this or this, so I did use the function and I found and here the absolute minimum, here the absolute minimum, here the relative minimum and relative maximum. Now, I'm not really concerned with the y values for these. For these, I really only want the x values when I'm talking about the intervals of the domain for which the function is increasing or decreasing. So those are the inflection points for these, and they happen to be absolute mins or relative mins and maximums. I want to make a point here. If I just did this in my calculator and didn't actually look or pay attention to the graph, that's 2.05 times 10 to the negative 6 is what it shows on the calculator. It doesn't show as 0. This number is so close. It's not exactly 0, but it's so close that when you round to the nearest hundredth or tenth or even thousandth, it is essentially 0. We know that it is exactly 0 from the function if we were to solve for the y-intercept for this graph, but you might see this on your calculator, so pay attention. Don't just write numbers down. Pay attention to what's at the end of that number as well. All right, so on this, prior to that point of inflection, that absolute minimum, this person was walking downhill. So the function is decreasing from negative infinity to 0. And then from 0 on, it's increasing from 0 to infinity. For the next problem, I have a relative minimum and a relative maximum. From left to right, this function tends to be going downhill, but that's only to this relative minimum and from this relative maximum. In this little section right here, it's actually increasing. So let's do the decreasing sections first. Decreasing all the way as far off the graph as I can see, negative infinity up to this relative minimum, which has an x-coordinate of negative 0.6. And it's also decreasing from this relative maximum of 0.6 all the way to positive infinity. For our increasing behavior, it is simply increasing only on that interval between the relative minimum and the relative maximum. So between negative 0.6 and 0.6. That's the only interval from this x value to this x value that the height of the graph is increasing as I move from left to right. And the very last one, we have the absolute minimum. So as we go from left to right, we are decreasing till we get to that point. So from negative infinity to negative 0.7. And that's the decreasing. And then we're increasing as we move from this absolute minimum infinitely up. So from negative 0.7 to infinity. These are intervals, they're parts of our domain. This is the part of our domain where the function is coming down or decreasing. This is the part of our domain where the function is increasing. When we write intervals for a domain, we must use x values, not y values. Again, the learning targets for this lesson were to be able to classify and estimate the extrema, the relative and absolute maxima and minima, and also to be able to analyze the graph as increasing or decreasing or constant and write those intervals, those domain intervals in interval notation. This concludes the video lesson for these learning targets in lesson 1.4.